events. There's like you can see the dachshund races. Anyway, it's great to see people come inside on a day like this for a physics lecture. But there's been a lot of interest in the Higgs, Higgs boson so far, and we've got Professor Max Chertok here, intimately involved in the experiments at CERN that discovered the Higgs boson, and I'm looking forward to hearing his talk.
Thank you. Thank you all for coming, and welcome to the physics department if you're just making your way here on picnic day. There was a little bit of a snafu with the agenda, which is why more of you are not in the audience, but we're very happy that you made it. So we'll hope to make these really interesting talks for you. And feel free to stop and ask questions at any time, especially the younger members of the audience. So just shout out a question or raise your hand and make sure that I see you, and I'm happy to answer any questions that you have. So I'm going to tell you about the Higgs boson and beyond. So in particle physics, high energy particle physics, we study the fundamental forces of nature. And the one that we know a great deal about from many years ago is gravity. And it's kind of amazing, right? This little guy is not touching the Earth, but feels the force of gravity. And there's something very deep about that we're still trying to understand. So it turns out that gravity is the theory and the physics of the gravitational interaction is some of the least well understood physics that we know about. So we're actually going to ignore gravity for the rest of the talk and move on to the electric force. Okay, so the electric force, we have little particles like electrons and protons and particles like that that have charge. And why is this little kid's hair standing on end? Any ideas? Yeah.
Because of static electricity?
Static electricity. So his hair is full of static electricity, and all those little electrons are pushing apart. They don't like to be near each other. And this is one of the forces that we study in great detail in particle physics. Now, along with the electric force, there's also something called the magnetic force. And magnetic force, well, at first glance, it's a lot different than the electric force. But on the other hand, what happens if we have two magnets and we try to put the norths next to each other? They repel. Okay, so there's this repulsion and attraction that's something like the attraction and repulsion that we have in the electric force as well. So there's some connection there that we need to study in more detail. And then we get to some very interesting, very short-range forces that have to do with the tiniest particles in nature and how they interact. And the first one's called the strong nuclear force. And okay, this is not made out of this super glue does not use the strong nuclear force. I just like the picture. But the strong nuclear force binds the quarks into protons and neutrons, and it also keeps the protons together inside the atomic nucleus. It's a very strong force, and it's one of the reasons why the sun shines. Okay, so the sun's shining is partially due to the strong nuclear force. It's also due to the other nuclear force, which is called the weak nuclear force. So it turns out that for the sun to shine, we need both the strong and the weak forces. And fortunately, the weak force is there because otherwise the sun wouldn't last very long. But along with the sun shining, this is Madame Curie, a very famous physicist that won the Nobel Prize for discovering natural radiation and studying radium and so on. And radioactive decay is governed by the weak nuclear force. So one of the things that we find out is that the more we study a couple of these forces, the more we realize the deep connections between them. And so we say that forces are unified. And for example, we now know that it's not electric and magnetic separately, but there's one force called the electromagnetic force. And we have a beautiful theory with equations that explain that in perfect agreement with what we measure. Now we can even get more sophisticated, and we can bring the electromagnetic force in with the weak nuclear force and come up with something called the electroweak force. And that seems really crazy, because how can magnets and kids' hair standing on the end be compared with nuclear radioactive decay? And it turns out that there's a deep connection between these two. And the question is, well, what is that connection? How do we make that connection? And that's where Mr. Higgs walks in, and Mr. Higgs comes up with an idea of how we can connect the electromagnetic force with the weak nuclear force. But if we're going to talk about Mr. Higgs, we also have to talk about his partner, and not really his partner, his competitor, Mr. Englert. Okay, so Mr. Higgs was not the only person to come up with the idea of the Higgs boson, and Mr. Anglaire was another one that was instrumental in the mid-60s to discover how that would work. This is just a precursor for what I'm going to show you later. Mr. Higgs actually visited my experiment. This picture was taken about 5 or 6 years ago, so we said that we had discovered Higgs at our experiment because the man himself came to visit. Okay, so what does the Higgs do? Well, it generates mass, and the idea is that there's a field associated with this Higgs, and it permeates all time and space. And particles interact with the Higgs field and acquire an effective mass. And so when you go skiing in heavy powder, and we hope we're going to get some heavy powder next year, up at Lake Tahoe, you're slowed down by your interactions with all the wet snow and the heavy snow, and you're kind of plowing your way through the snow field. And if you want to think about it that way, the Higgs is like a field of this very dense powder, and you're sort of acquiring a mass, you're slowing down by going through it. Now, there are other particles. This is a person like you or me. I could just say, oh yeah, this is a picture of me, but you wouldn't be able to tell. But without the Higgs, all particles would be massless and travel at the speed of light. And so the universe would not be able to clump together and would be, have no structure. And we can imagine that there's some particles like this beautiful bird that just sort of skate along the top of the snow or on top of the ice, and they hardly interact with the Higgs field at all. And the particles that interact very weakly with the Higgs field have light mass or no mass, and the particles that interact very strongly with the Higgs are very heavy. So that's the idea of the Higgs. And this is my first kind of plug for our local group. So we have an eminent theorist, Jack Gunyon, who wrote a book in 1989 called The Higgs Hunter's Guide. So this was many years before our discovery. And he and his friends, his theory friends, wrote a book that was really the instruction manual of how you might go about in search for the Higgs. Because the Higgs was a hypothetical particle at that time. We didn't know what its mass was. And these guys figured out how to do it, and it was led by our own Jack Gunyon. And you may remember there was also the Hitchhiker's Guide to the Galaxy a mere 10 years before. So we have our recipe books for important facts of life. So that sort of takes us to the pre-Higgs discovery standard model. And what we understand is that we have ordinary matter made up of atoms, and the atoms have a very tiny nucleus surrounded very far apart by an electron cloud. And we believe these electrons to be fundamental particles, which means they have no size and they have nothing inside them. The nucleus itself is actually quite complex. It's made up of a bunch of protons and neutrons that are bound together by the strong force. And each one of those protons and neutrons is actually made up of quarks and gluons inside. And as we go from here to here to here, we're going down by almost 1 million times in size each time we go down. So 100,000 times smaller to get to these different steps. And so one of the things we do in particle physics is we study the up and down quark and I just realized I didn't turn this on today. How's the sound? Am I yelling loud enough? Okay, so I won't bother. So one of the things we do is we study these tiny little particles and we study the interactions of the particles. So this is where we do our research, and this is called CERN, the European Center for Particle Physics. And the lab site is over here. Here's an aerial photograph of the Geneva, Switzerland area. And this is the giant Large Hadron Collider, 27 kilometers around. It's so big that light and protons can only travel about 10,000 times every second around this ring. And there's a Swiss side of the lab, there's a French side of the lab, and in fact, our UC Davis experiment, CMS, is on the French side. So it's about a 10-kilometer trip from CERN to get over there. Here's Mont Blanc, the highest mountain in Europe. And this is what the experiment looks like. It's really gargantuan. And when I say it's the UC Davis experiment, of course, it's us and a bunch of our friends. So 39 countries, 169 institutes, 3,000 scientists and engineers, about 800 students. So it's wonderful training for students. We have a lot of UC Davis students either working here or stationed at CERN working on the experiment there. The thing is absolutely gargantuan. It weighs as much as the Eiffel Tower, 15 meters by almost 30 meters, and we've got this gigantic magnet I'm going to show you on the next page. The groups from the United States work on a whole host of elements of this detector. I'll give you some more details about that. So this is a bunch of us from Davis that went and visited several years ago when the solenoid had just been commissioned. And so you see how big this thing is. It's a 6 meter by 12 meter superconducting solenoid. It's the largest one in the world. And when we don't use it, we rent it out as a skateboard park. It's actually very fun. So anyway, this is a bunch of us, and the thing is really gigantic. Now this is all filled in with particle detectors. This was before those inner parts had been installed, so it looked like this. And UC Davis has been on this experiment for a very long time. It's so big, you can imagine it takes a long time to design and build it. It took almost 20 years. And we joined in 1992. That was before I got here. So our group joined. And we've been working on the smallest parts of the detector and the largest parts of the detector. And actually now with Professor Mulhern, who will give you the next talk, we also work on the fastest parts of the detector. So anyway, these are all state-of-the-art components. This is a silicon pixel detector. These are gigantic muon chambers that Richard Breeden is proudly standing in front of right here. So Richard is here. And this is a bunch of us, all from Davis, that installed the pixels several years ago. So one of the fun Davis activities is we're the ones that actually install the detector. And we get to work right here with hard hats and right near the beam height. It's pretty neat. Now clearly the beam is off when we're there, so there's no worry about safety. We still wear radiation film badges. We still have dosimeters to make sure everything is safe. But of course the beam is off when we're there. The magnet is also off. So we worked on many different parts of this. And we were there when the machine turned on, and here's a little animation of two bunches of protons coming together at the center of the detector. We build the detector right around the interaction point. And these are the various detector components, and they're being removed so you can see better. And what we hope for is that a proton from one of the beams hits a proton from one of the other beam and creates new forms of matter. And those new forms of matter typically are very unstable. They decay, and what we observe in our fancy detector, which is like a gigantic high-speed camera, is the decay products, and we're able to do our physics based on those. You like that? Oh, you want to see it again? Okay. So let's see it again. So this is just one event, and I'll give you a little bit of math on one of the following slides to show you how many collisions we actually look for to find the Higgs. And so every one of those is a different charged particle traversing the detector. A lot of them are curving because we have that big magnet, and we're able to figure out what all those different particles are. So pretty cool. Okay, so how do we search for the Higgs? It turns out that we need a lot of data to search for the Higgs because this thing is a very rare occurrence. So searching for the Higgs became the holy grail of particle physics. So what we do is we collide protons at very high energy at the Large Hadron Collider, and we repeat this 40 million times a second for about a year or maybe 2 years. And so in 1 year, Mike, how many seconds in a year?
I think it's something like square root of e to the x squared times 7.
Thank you, perfect. So about 30 million, roughly, and we're doing this 40 million times a second. And if you multiply these out, you find out there's about 100 trillion collisions. So what we're looking for is a few Higgs particles, like a real beautiful signature that this was a Higgs. And we're happy if we get a couple hundred out of this 100 trillion collisions. So in every one of those collisions, we look for a distinctive signature of the decay products as we record it with the detectors. So we can measure electrons, photons, quarks, muons, and we can measure their energies and their momenta. So the energy is how much energy they have, their momenta is which direction they're traveling in. And so this is kind of the basic physics quantity that we need to figure out exactly what took place. So we analyze all the tracks and the energy deposits from these collisions, and then we try to classify events, like, oh, this is interesting, we better group this with other interesting events, maybe this is the Higgs, or maybe this is something else. And we do that, and many students work on this, many professors. It's a lot of work, it's a lot of fun. And you know, when you collide protons, you don't know what you're going to get. So the theory tells you you're looking for the Higgs, but maybe we'll get lucky and we'll get a duck and a fish. But we didn't get any ducks or fish. Yes?
How do you analyze all those collisions? You have a lot of grad students, or just
We have a lot of grad students, and we have a lot of computer power. And every one of those events gets written out to a computer file. We can't measure it all, exactly. So what we do is we try to select the the most interesting events as they're coming through. So one of the things about the fastest part of the detector, it's called a triggering scheme. And what we try to do is select the most interesting showers of energy and particle tracks and signatures, because those are the ones that we want to analyze later. But you're absolutely right, we can't even measure all, we can't analyze all of them, but we measure quite a few. Because every one, this is one event. So you see, you're absolutely right, that this one event has hundreds of particle tracks. And one of the things that we found really interesting about this one is that along with all those particle tracks, there were two very high energy photons. Okay, and one of the things that Jack Gunyon taught us many years ago was that to search for the Higgs, we should look for the Higgs going to 2-photon decay. And so we built a very... The computers are pretty fast, but not as fast as we need to analyze every one of these. Very good. It's 40 million times a second, and so we can't keep them all. Anyway, this is a really telling snapshot, and it's really fun as a grad student. You can look at this on your computer, you can rotate it, you can zoom in, you can click on all the tracks. This is what we call our event display. And here's another one. This is a completely different type of event where we have two high energy electrons and two high energy muons. And that's another smoking gun for the Higgs particles. So we were very excited as we started to see these particles coming through our detector. So we waited, we took data, we kept the experiment running, and here's a little graphic of one of the ways that we search for the Higgs in the 4-lepton channel. And this shows you actually how the statistics came in as the run went on. And so this takes a little getting used to, this kind of a plot. This is just showing the mass of all of the important particles bunched together to look for a new bump. And we understood this blue bump over here, that wasn't new physics. We understood this bump over here, but this was brand new. And so this red excess over the blue background is a very important part of the Higgs discovery. Okay, so again, let's watch that again. This actually shows you event after event which events were coming in as we ran the experiment. We actually ran at 2 different energies, and that's what we ended up getting. So you see, it's not a lot of events here at all. Now, Jack Gunyon told us to look for the Higgs to gamma gamma. This doesn't look impressive, but in fact, if you look carefully, this really is quite a nice little bump. Yes?
Can you move to the previous slide?
This one. Yep.
So there is a lot of little bump there, and between the red and the blue, and there is a dot there.
This one?
Yeah.
Mhm.
What is the
So we analyze these statistically. Notice that for every dot, there's an error bar associated with it. And those error bars are large enough that any one fluctuation like that is not significant. It may look more significant than it really is. And so if you can get several bins in a row where you have an excess, then that's something very important. And very, very crucial to this whole result was that we got a bump here at about 125 GeV in this 4-lepton channel, and we also got a bump at 125 GeV in the 2-photon channel. So 2 completely different data sets, 2 completely different measurements, and if you can correlate 2 results like that, that gives you very strong evidence that you've discovered a new particle. Other questions? Okay, so we made a t-shirt. I almost wore the t-shirt, and I chose not to. So we got the t-shirt out of it, and the theorist got the Nobel Prize. So maybe that's the way it should be. You can see Peter Higgs has his eyes closed. You can't believe that this moment has finally come. There was a really nice ceremony at CERN before the Nobel Prize ceremony. So this is Peter Higgs and Francois Englert, who shared the Nobel Prize for the Higgs. So they can't give the physics Nobel Prize to thousands of people, and so we do not get the Nobel. We don't get to share it. They don't divvy up the medal by 4,000 little pieces, but it would have been nice. Okay, and so that takes us to where we were after that announcement, where we now understand that we have fundamental particles called quarks, and it turns out there are 6 of them, fundamental leptons, and the electron is a prime example of the lepton. And with our electron, we have a neutral partner called the neutrino, and for the electron, we have a heavier electron called the muon, and even a heavier one called the tau. And each one of these has its own neutrino associated with it. Neutrinos are another topic of study at UC Davis. And so we have 6 leptons. It's very interesting. We also have 6 quarks. These are the guys that make